Hello, welcome to Office Hours. This is Unit 2 Office Hours. What I'll do is I'll look at the forum, see if there's any unanswered questions, and take it from there. But if you sign in on to Office Hours, by all means, feel free to ask your question and get that answered for today's Office Hours. Thank you those whose question has been answered. You've closed it or you marked it as such. This helped me navigate and look at to better find out which questions still need to be answered. Someone's asking me how I'm doing. Yeah, I'm doing good today. How about you? Hope you're doing good as well. I know that link is still missing, so I'm going to see if I can fix it right now. Okay, so the floor is open for questions. I'm currently uploading the missing video to the Google Drive, so hopefully that'll be up in a couple minutes. Thank you for pointing it out. Okay, so this question here is, why do we use uppercase X and lowercase y in the format f of x equals y? Is it only a strong convention? So the reason behind that is we are trying to signify to you that X is a matrix or a two-dimensional array, to be more specific, to be more detailed. In other words, have rows and columns. Y, on the other hand, is just a vector. It only has one dimension. In this case, the number of rows only has one column. You can view it as just a one-dimensional array. So that's why we have to use a lowercase y. Regarding, is it a strong convention? I would say it's a rather strong convention. It's not written in stone. So it's, I guess it's sort of, if you look at its spectrum of conventions, it's a popular one you're going to see. Keep in mind, other people may not always adhere to it. This also differentiates, if you see a lowercase x, oftentimes that just means one observation, one row. Okay, so I believe the link has been uploaded. Let's see if I refresh the page. Is it showing up? Yes, it has shown up, so I'll go ahead and indicate that. Can we not use a format? Will it work? Can we not use a format of f of lowercase x equals capital Y? I mean, that right there can be a little confusing because some people might be confused about that. They might view Y as a matrix there. I mean, it's just a convention. Keep in mind that it's just a convention. You can use whatever notation you want. However, I would stick to what we suggest. At least we'll help you go through the lecture notes because we try to adhere to that convention throughout the notebooks. Okay, there's a question here. How does the fit and predict methods work under the hood? Can we unfurl that? Okay. So when you invoke fit, what is happening is that it's taking x and y, or it depends on if it's a transform or a predictor. But let's say it's a predictor. It's getting x and y, and it's doing whatever it needs to do to solve for model parameters. For example, if you're using linear regression, it's taking x and y, it's running it through an equation to figure out what are the beta coefficients. These are the model parameters needed for linear regression. That is what's happening underneath the hood when you call fit for a linear regression. What happens exactly when you invoke fit will vary depending on what type of model you have. But generally speaking, when you invoke fit, what is happening is that it's solving for the model parameters. It's solving for the model parameters. It's solving for everything that is required for you to make a prediction. So generally speaking, when you invoke fit, it takes x and y, everything it needs to calculate a prediction. When you invoke predict, what it's doing, it's taking each observation in x, running it through the model, using the parameters it had solved for during fitting, and generating a solution, generating a prediction. So for each row, it's calculating a y value. That's generally what is happening underneath the hood when you invoke predict. For transformers, very similar. The fit method of a transformer, it's going to learn model parameters that are required for transformation. When you call transform, it's going to take each observation x and transform the value. What do you mean by can we unfurl that? Can you elaborate by that? Okay, so can we see the program that is being used in the method? Yes, you can. It's all open source. It's all open source. You can view that. No problem. You can follow this link there. You can look at what's happening. There it is. This is just the Ridge model. So every time you use Ridge, you can look at the fit definition. So you can look at exactly what's going on. Okay. Anyone out there who has questions, feel free to ask. The floor is open. I don't believe there are any unanswered questions on the forum. Someone is asking, Dimitri's asking, can you briefly describe how you can deploy a machine learning model? Are you referring to kind of the demonstrations that I showed in the first lecture where I had that web app where you put in some fields and you're able to predict whether someone survived, or some sort of sentiment app where we can put in the text block in the box some text, hit run or something like that, and gives you back some sort of sentiment? Is that what you're referring to? Yes. Okay, cool. So in fact, we're going to go over that at the very end of the course. At the very end of the course, week 8, you will see lectures regarding that material. So I'm going to hold off, and we can, at that point, we can discuss what's going on there, but we will have lectures at the end of week 8 regarding that subject matter. Briefly speaking, we'd have to serialize our model, basically create a file representing our model, and use some sort of web framework. Something like Flask is what I use there. Use Flask, deploy the model, and what's basically happening is that the Flask app is going to handle any inputs from a user. It's going to take those inputs, we do some sort of processing on those inputs, and then run those inputs to the model, get a response, and report it back to the user. So it's using our model. We've trained the model, we've serialized it. I believe there'll be some lectures about that concept. And then every time someone needs to use the model to make a prediction, we load it back up, run it through some inputs, get the value, report that back. That's all done using Flask and a trained model using scikit-learn. In fact, the demonstration we do at the very end is showing you that sentiment app regarding tweet sentiment. So I'll set it up kind of like a case study where we'll say, okay, we want to do create an app to do tweets. So, we create the app, we deploy it, we use it on actual Twitter data, things like that. So so that's all I want to speak about that at the moment, but we will get to that, and we can talk more when the time arrives. I see someone said that's very lengthy for the kind of job it is doing. Yeah, I guess it can be rather verbose, but it's a rather mature package, and it's running through a lot of cases of what type of algorithm to use exactly. I believe what it's doing. It's checking a lot of things. It's doing is checking the type of input. Depending on if it's a sparse matrix, it might be a better algorithm to use instead. So it might seem like it's a simple model, but there's a lot of implementation details underneath the hood to get the most out of that model. But yeah, I agree. You can look at it as it can be a bit daunting there. NLP requires a lot of English vocab, don't they? So I would argue that in the field of natural language processing, it's more skewed on towards English. But however, when we deal into natural language processing, we'll deal with a tool called Spatie, and there are language models apart from English and Spatie. So yes, a lot of development for NLP has been focused on English. That's just the nature of the situation. But there are some of these packages have other languages supports. Someone is asking, how are the translation platforms work? You're talking about in general, how does language translation work? Yeah, definitely the grammar aspect, the difficulty lies there. And, I'm not full disclosure, I'm not an expert in translation services. And there are a lot of state-of-the-art tools that are going on there, but a lot of them are aimed at determining grammar. Other translation tools, what they're doing is that they're using something like Word2Vec, something similar like that, where if they've trained it on a large English corpus, and let's say a large English corpus, and in there they have a vector representation for a word like pig. And then you can figure out the equivalent word if you were to do so on a different corpus of a different language, and in that space, what vector is closest to. and you would pick up the translation that way. Of course, this is just a word-by-word translation. It's not going to pick up the grammar. You can also, things that it's doing is using some sort of looking at words around their neighborhood and using that to predict what should be the next word. A little bit more of expert rules, like expert systems, to better define the grammar. So it's a rather difficult task. Unfortunately, we don't get into that in the lectures, but hopefully you'll learn enough NLP so you can go into those subjects if that is of interest to you. Okay, so the floor is open. So if anyone has any questions, feel free to ask. The floor is open. All right, the question here is, we need to do data munging before we pass our model to the fit and predict methods, don't we? Oftentimes, there's a lot of pre-processing involved to get data into the format for the predict and the fit and predict method. So yes, that is correct. And that's what transformers are there for. If you can systematically write the munging and processing, encapsulate into a transformer, you can use something like pipelines to encapsulate the workflow. Someone saying machine learning is very different from traditional statistics and econometrics. We are not doing any hypothesis testing, normality checks, and so on. Yes. So the reason behind that is because machine learning is more focused on predictions. more emphasis on correlations rather than causations. Standard statistical approaches, those traditional, standard, tried and true statistical approaches, have a lot of emphasis on causation rather than correlation. With machine learning, the ultimate goal there is to have a strong predictor. Given certain fields, predict the value. It's not, really exploit and find the correlation between those inputs and the output, creating mapping from the inputs to the output. So definitely more emphasis on prediction. If you're looking for, more, to establish causation, then really those machine learning techniques are really not meant for your application. Someone says here, the California housing, how can we decide upon which factors are most influencing in order for us to determine how we shall design the model? Can you please explain? Okay. So in this case, you can do some sort of data exploration. We kind of do this in the video, I believe, looking at the different features. And since we're looking at prediction, we were concerned about, since I believe we're using linear regression, we were looking at the correlation coefficients of the features with what we're trying to predict. So in this sense, we are looking at which of these features we think would help us the most in our prediction task. And I believe we go into, let me just double check. I believe we start designing, or we encourage you to design certain transformers for to engineer some of those features. And sometimes it requires domain knowledge, familiarity with the features, to start generating additional features based upon your original features. Our target price is I believe the median home income, because what it is a data set, I believe, by census block, by census block, and you're trying to predict the median home price in that particular census block. Regarding back to the California one, in some sense, we want to use, at least initially, all the features we have. Because in that problem, we only have, I believe, 8 features, and that isn't really a lot. So the emphasis there is perhaps to keep as many features as possible, but to also consider maybe there's some features we should generate instead. And right there, it just requires playing around with the data, using some data analysis, some data munging, some data wrangling to look at some important features. Which features are more important, and also generate any additional features that make sense given your expertise, given your familiarity with the domain. For example, you can generate a feature you think might be very predictive in the sense that it's based upon how far away you are from some sort of city center. So someone you're asking here is, we exclude the luxury homes because most fitting and fixtures may outweigh the contribute as outliers in the data set. Well, I mean, in luxury homes, then the question is there any signal in the data set to signify that that is a luxury home? I would agree that it'd be an outlier if there's a luxury home in an area where there's not many luxury homes, but maybe that luxury home isn't necessarily an outlier because it's close with a lot of luxury homes. So if you're concerned about outliers, then you can look at different metrics. You can use like the mean absolute error instead of the mean squared error, since it's less equal to outliers. You could look at some sort of initial model that's going to flag outliers. So there are outlier detectors in scikit-learn. We'll talk about those in future weeks. You can use some of those outlier detectors. You have to tune them, of course, to clean out your data. Remove those outliers before you train the model. So it'd be one process right before you train the model in your data set by learning what those outliers are and removing any potential outliers that might be in your training set. So in short, you would use some sort of outlier detection technique to see if you can find those and remove them from your data set. Yes, there are lie detectors. The 2 most popular ones is Isolation Forest and One-Class SVMs. We'll discuss those in future lectures. Someone's asking, are the mini projects in Unit 2 more difficult than the ones in Unit 1? I'm going to let you decide that. As there are so many predictors, how can you choose proper one for a particular problem? Are there any blueprints or just go try them all? So it might be tempting to go try them all. And I would first ask yourself, well, the first thing is I like to say is very rarely does a problem that requires data science and machine learning, very rarely does it exist in a bubble. In other words, very rarely is the prime objective is to have the best model possible. The best accuracy, best prediction, best regression value, R-squared value. Very rarely that's the case. There's a lot of, business things to consider, a lot of external constraints that are going to impose on the problem. So the first thing you want to do is, what are those constraints? Write them down. Hopefully someone who is a product developer or manager can articulate to you those constraints, because you're going to use those constraints. Those constraints are going to factor in ultimately what model you choose. So there's several things to consider. So if there's no constraints, then really it's just to try anything as possible. You can really divide these models into two branches, really. You have people use the word shallow and deep, but I don't like the word shallow because it implies that some of these models aren't so great, and that's not necessarily the case. So in some case, you would want to first look at non-neural network models and see how far you can go there. And the reason why I said is because neural network models tend to be harder to construct and to debug. They tend to be very black boxes and very hard to debug and understand what's going on. So because of that, you may not want to necessarily go that route. A lot of effort can be spent there, so much effort that it was perhaps just better to stick with the non-neural network routes. Within the non-neural network routes, if in generally, I would say gradient boosting is the way to go. If you were to choose what model to use that will get you the best prediction, I would use some sort of ensemble tree-based model. Think of gradient boosting or random forest, something like that. Will probably outperform all the other models, generally speaking. But let's consider the other constraints that might be involved. Perhaps it's very important for you to explain to someone how the model works. So we need high model explicability. So in that situation, then you may want to avoid something like ensemble methods like gradient boosting trees and random forest, because they're a lot harder to explain to someone how they work. A decision tree is very easy to explain to someone how it works. Linear regression is very easy. You have a functional form for the model, so it's very easy to determine how it works and explain to someone how it works. So that's a constraint there, explicability, that's common imposed on machine learning models. Other thing that's involved is time complexity. Time complexity in terms of training and prediction. I get into this when we talk about specific models. Typically, how does the training time scale with the number of inputs? And this will be a consideration of which model you choose. Certain models don't scale so well with increasing your data set size. For example, SVMs, they don't scale really well with number of observations, n squared to NQ time complexity for training. So because of that, if you have more than 10,000 data points, 100,000 data points, you're not going to want to use SVM. So you would ignore them altogether, unless you want to do some sort of kernel trick, which we discuss in Notebook. That's for a later discussion. So that's another constraint, the size of your data. Let's see what other constraints might be. Yeah, sort of prediction times. So that's, the main thing there is explicability, what you're trying to get out of your features. There's actually, scikit-learn does have a very crude, I can show you this, scikit-learn picking model, or it's not a model for, let's see, choosing the right estimator. There you go. So I'm going to I'm going to put this here in this channel here. This is kind of a path you can take to figure out what's a good starting point for a model. However, I wouldn't take this as gospel. I wouldn't take this as ground truth. And I would definitely not take this as truth, more as a guide. So you can take a look at that to figure out what's made a good starting point. But just keep in mind, these are generally suggestions. In general, if you're really trying to get the most prediction, don't necessarily go into the neural network route unless you've spent some time trying to do some sort of ensemble models like gradient boosting trees or random forests. That was a bit of a long answer, but hopefully that gets to your question. And as you go through the module, I might emphasize these points, and some of these things might click or might make more sense. We can always revisit this topic later on, but I think that's enough to get you get your question answered for the moment. Hopefully that is the case. All right, the floor is open for questions. If you have any questions, feel free to ask. The floor is open. Okay, so how to use Flask? How do we install it? And or can we use it from inside the Python environment? So you can do something like pip install Flask, something like that. I think you might complain and say you have to use something like user flag or something like that. Something like that. How to use it? That I'll save that for. Yeah, so you can do. Let me just let's see. I'll save that for those lectures. But let's see if I can give you some. There's some links I like to use. On that link, pretty helpful to get you up and started running with Flask. But yes, to answer your question, use it inside the Python environment. It's a Python package. It's a Python web framework. So it's going to allow you to create web apps using Python. Someone is asking, what is the recommended IDE for working for larger projects after experimenting in notebooks? This is one of those things where it's a matter of taste. I use Emacs. Other people like to use Vim. I can tell you some popular ones. A popular one is Sublime. A popular one is, let's see, what's the other one? Atom. So let me just write those down. Something like Emacs. There's Vim. Sorry, oops. Vim are ones that have been popular. Those have been traditionally, rather popular text editors in general. But a lot of people like Sublime. People like Atom. People like to use Spider. I haven't tried it out, but take a look at it. So just spend some time. Like I said, I personally like Emacs, but that has a large learning curve. It takes a while to get used to it. Some things like Sublime and Atom are a little more easier to use, so you can get faster and up and running. So I kind of recommend just try those out. But it's more of a matter of taste. But take a look at that. And those are in general purpose editors. I believe Spider is more focused towards Python. So my recommendation is to move away from specific text editors or IDEs for a particular language. And the reason why is because you have to learn an IDE for this language, for that language, for that language. It's a more efficient use of your time to learn one text editor, know it well, and have it applied for any programming language. Okay. So which text editor do you suggest we use? I would look into Sublime or Atom if I were to make a recommendation. So I'm going to avoid, I really want to avoid, giving, this is the one you should use. But try those out. Try out Spider. I think, and it looks like Dimitri, you're saying that Spider can display pandas, data frames, and NumPy arrays in a spreadsheet style format. So that can be very nice. So that can be really good and nice. But my reservation is that it's nice if you can learn one text editor and have it uh, be applied to any other programming language. But it's ultimately you to decide. I just let you know which ones are the popular ones, give you some facts and my takes on them, and then ultimately you'll make the decision what makes best sense for you. So someone says, don't we miss the debug capabilities of the IDE if we stick to with text editors? Not necessarily. A lot of these text editors, text editor might be, they're not purely text editors. There are a lot of things you can add on and incorporate to these quote text editors to give you things like debugging capabilities, to do auto completion, to do automatically looking up doc strings, documentation, very nice macros to do a lot of common tasks. So they're not just simply text editors how you would deal with something like WordPad or Notepad. They're souped up text editors primarily geared towards programming. And there are things you can install and add on to these text editors to give you powerful capabilities. Okay, the floor is open for questions. So let me know if you have any questions nearer towards the end of office hours. So sneak one in if you got time. Okay. Any last questions? If not, we'll go ahead and end office hours. And yeah, thank you guys for coming. Thank you for the questions you asked. And we'll hear from you tomorrow if you guys sign in. Take care, guys. Have a good rest of your day.